Let's start with secants and tangents, and this time I want to focus right now on the secant being to an even power. So what I want you to remember is that if you would pick u to be the tangent, your du will be secant squared dx of x dx. So what you would want to do is separate the secant to the fourth and pull a secant squared out of that. And I'm going to write a tangent here, and I'm going to write the secant squared again. I'm moving it in that, putting it in that order so that you can see right here. This is your du exactly. And so, whoops. So what you get is the integral of the secant squared. I'm going to leave this one alone. Actually, let's talk about it before we do anything. The tangent, you see, is going to be substituted by this. But that secant there, you have to remember one thing. That is the fact that cosine squared, just one thing you have to remember, plus sine squared of x equals 1. If you divide every term by the cosine squared, that turns into a 1 plus, this is sine over cosine is tangent, so this whole thing is tangent squared. And 1 over cosine is secant, so this is secant squared. So you see this secant squared. Let's grab another color, probably this one, maybe that. So using that color, almost the same. My secant square here, I'm gonna, it looks almost the same. I'm gonna change to 1 plus tangent squared. So it's gonna be 1 plus tangent squared. So it's gonna become 1 plus u squared times tangent. That's gonna be another u. And this secant squared of x dx is gonna become my du. So putting it all together, tangent it becomes u is 1 plus u squared times u times du. So right here, my du is this, and my tangents are going to be substituted in there. And so I can now just distribute, write it as u plus u cubed, distributing, and now I can integrate u squared over 2 by adding 1 into the exponent and dividing by that new exponent. U cubed is going to become u to the fourth by adding 1 to exponent over 4, and don't forget your plus c. Taking in back my substitution, which is tangent. I get tangent square of x over 2 plus tangent to the fourth of x over 4 plus c. This one was pretty much or very straightforward, but now why do we need an even power of secant? Is because you see when I separate it I need a secant squared, but if I would be left with a secant here, then I cannot use this nifty little way to do it. Now you can even, it doesn't have to, tangent doesn't even have to be multiplying, and that's true even for when you have the odd powers of the cosine and sine. I forgot to mention that the powers don't even have to be positive, they could be negative. So let's do another one where we change this one, just modify it ever so slightly by putting a tangent in the denominator instead. Oh, well, I did my perfect last one, then I dropped it at the last second. I'll delete all that. And so let's change this up. And let's put the tangent here. Maybe a tangent, I don't know, cubed or squared? Square, why not? So it can also work like that. You do the same thing. So you go ahead, whenever there's a secant to an even power in the numerator, the secant does have to be positive though. So just be careful with that. Actually, take it back. It could be negative. I'll show you how you deal with that in a second. I take it back. I hadn't thought about that before, but it turns out that you can actually deal with it. So this right here is going to become my du whenever I do my u substitution. My u substitution being the tangent, as we said before. Du is just going to be my secant square of x dx. And I'm going to remind you that 1 plus tangent squared of x is secant squared, because I'm going to need one of those. So what goes where? Well, this u is there's gonna be going 1 here, and I'm gonna be using 1 over here, and my du will be already chosen there. All right, so let's take a look at what happens. I'm gonna substitute in the secant squared with my 1 plus tangent squared. Over tangent squared. And then times secant squared of x dx. I can distribute that tangent if you want. It's going to be 1 over tangent squared. Let's put in the substitution in. 1 over u squared, and then when you distribute it to this one, plus 1 du. And this is just going to be integral of u to negative 2 plus 1 du. So what you do is you add 1 to the exponent, so you get negative u to negative 1 plus u plus c. So you could write this one as 1 over tangent, or the reciprocal of the tangent is just cotangent. So you can write cotangent x plus tangent x plus c, taking back your substitutions. That's another way to use it. So where the tangent, it has a negative exponent. All right. All right, so what I would like to do in this situation is do a u equals secant of x. And then the du, remember, is going to be secant x tangent x, the derivative of the secant, and then dx. So I'm going to separate out one secant tangent. So I'm going to pull one secant out of these 3. So I'm going to be left with 2. I'm going to pull one tangent out of this, and I'm going to have, and then I'm going to have secant tangent dx. So you see what I did was separating out or forcing my du to appear there. So I'm looking for a secant substitution there. So notice the first term is going to be easy, but then you remember that 1 plus tangent squared, as we did before, equals secant squared. And then you solve for the tangent square as tangent squared, equals secant squared minus 1. So I can plug in the secant squared. Stay like that. You know what? Let me start putting u's, because I don't think I can fit this whole thing. So instead of secant squared, I'm going to write u squared. Instead of the tangent squared, if I put my substitution in here, it would have been u squared minus 1 in this particular case. So I'm going to plug that here for the tangent squared. Sorry, it's just I was going to run out of space if I would have done it otherwise. Now du is just secant tangent, and that then becomes the integral of u to the 4th minus u squared du. So in this case, we get u to the 5th over 5 minus u to the power of 3, or u cubed over 3, plus c, which is going to be tangent to the 5th minus tangent cubed plus c. So that's another case. So we had the case when secant is to an even power, independently of what the tangent is doing. then because the substitution would be u equals tangent, now whenever we have that the power of the secant is odd and the tangent is also odd. Why is that? Well, because I need to pull out a secant and a tangent, and I need to be left with an even power, because this even power is what I can transform by using my identity. So that's when both are odd. So now let's talk about the cases, the case when well, secant is odd, but tangent is even powered. And that's going to be the last possible case. So we exhausted the situation because we have secant is even. That doesn't matter what tangent is. We can take care of it by doing the u substitution u equals tangent. Now for secant being odd and tangent being odd, the substitution u equals secant works. Now when secant is odd and tangent is even, that one we will address now. So let's take a look at that. Eliminate all this, and we will change this 3 for a 2 to see how things do not work if we were to just try to simply say that u equals secant. If you try that, du will be secant times tangent. But you see, when you pull a secant and a tangent out of that, you get secant squared. Now a tangent, you have to pull one out of those two, and then you'd have secant tangent dx. So you separate it like that to separate your du as we had done before. But you see, your problem now is that you have a way to make u equal secant, but from this guy, you're not able to recover a you cannot substitute it in, because remember, tangent square is what you need to be able to substitute in with secant in any reasonable way, secant square minus 1 as we would need. So that's definitely not going to work. So I just wanted to illustrate that. And now what we're going to do, whoa, that was exciting. What we're going to do, I don't know what I did. I'm trying to pretend that I know what I did. I didn't. I don't. So what you're going to do is you're going to try to do an integration by parts. So now, what do you know how to integrate? So what you know how to integrate really well is your even powers. So make that your dv, because we just did it. Make it your secant squared. I'm going to pull a secant square and a tangent square of x dx. So that one I can integrate as in the case before, because these are even now. So what I'm left for my u for integration by parts is I'm missing one secant of x. You see, secant of x and secant squared gives me a secant cubed, tangent, tangent, dx, dx. So I have everything there, so I just have to now take my derivative. du is secant tangent, I apologize that I ran into this one. Now for b, I'm going to integrate this one. Remember, this is a u substitution. U equals tangent. Du is secant squared dx. Secant squared of x dx. So this is going to be the integral of u squared du. And there's going to be u cubed over 3, which is going to be a tangent cubed over 3. I'm just doing a quick, this you have to integrate using the previous case, the first case we looked at in this video, where you have even and even, or even for the secant, whatever for the tangent. All right, so now my integral is going to be according to the integration by parts formula. Let's call this one I, and I'm going to go like that. I is going to be uv, so it's going to be 1/3 of secant of x tangent cubed of x, just uv, minus the integral of, and v, I have a third here, du. So v du is going to be equal to, so 1/3 of tangent times tangent is going to be tangent cubed, and then times secant. Dx. All right, perfect. So that you say, well, So what have you accomplished so far? Well, not very much really, but I want to lower the degree. So you see the combined degree of these two guys is 1 and 3 is 4, and the combined degree of these ones is really 5. So I should be able to yeah, that's because I did it wrong. I had secant tangent. They have to be 5, so I can actually eliminate things out. Of course, this is a 4, if you notice what I did. V du. So V du is V du here is tangent cubed times tangent, so for secant of x. Okay, now that's gonna work out because now what I need to do is grab one of these tangent. You see, I want to compare two things. I have degree 4, I have degree 2 here. And as I was saying, the combined degrees should be the same, and that's where I was like, oops, I made a mistake here. Because here I have a 1 and I have a 3. They add up to 5, but I have to change it. And the way I'm going to do it to change this integral is I'm going to copy this part. And I'm going to change this. I want to pull out a tangent squared of this one. You say, why would you even do that? Well, I'll show you. What's going to happen is now the tangent square is going to match the one I have above. And this tangent square I'm going to change with my identity. You see, now I have these two matching. That's what I wanted. And it's going to be clear why I want them to match in just 1 second. Because what's going to happen is I'm going to get a multiple of I coming out of this integral. So I'm going to then move it out, that I. And I'm gonna end up with a combined degree of 3 instead of 5. So I start with a combined degree of 5. I'm gonna drop it to 3. Another integration by parts, and eventually I'm gonna get it down to degree 1 where I can actually integrate. So that's the goal. That's what we're trying to do here. All right. So now let's take a look at how do I do that. So remember my identity that I had. Let me put it over here a second ago, and we said that 1 plus tangent squared of x equals secant squared. Remember we wrote that? Okay, so tangent squared is going to be secant squared minus 1, and I want to substitute that in here. So I'm going to have that the integral I that I'm looking to compute is going to be a third of the secant of x tangent cubed of x minus 1/3 of an integral secant. And then instead of the tangent, I want to write secant squared minus 1 of x always. I tend to just say secant and just say the function, but it's always evaluated at x. Don't just write the function, because some people just write the function. A function without any argument is, in terms of our calculations, doesn't really make any sense at all. Sometimes we talk about the function f is continuous at, and we don't give it an argument or a value to evaluate it at. But that's not the case here. We're doing actually a calculation. We need to have x. So I say it incorrectly, but please do write dx every time. All right, so I'm gonna distribute these guys, and what that's gonna do is it's going to become 1/3. I should copy that and paste, but now I'm writing it, so might as well write it. Copy this part, and then minus 1/3, and I'm gonna separate these two terms out. So I'm gonna have secant. Distribute the secant first. So secant cubed of x minus secant of x, and then tangent squared of x dx. And you say, this is getting complicated and this guy doesn't know what he's doing, but I do. Let's hope. The secant cubed and the tangent we can multiply together, and I'm going to separate the integral so you can see what's happening. So it's kind of chasing our tails a little bit, but it's just that's the way these integrals go. So 1/3 of the integral of secant cubed, what was that? Cubed here of x, tangent squared of x dx, plus, when you distribute this, 1/3 of the integral of the secant of x tangent square of x dx. Whew, barely any room. Finally, all right, I want you to pay some attention here. You see this integral here in red is where we started. That secant cubed tangent squared of x dx, that is the same I. You see, so this becomes I, and then 1/3 secant x tangent cubed of x minus 1/3 of I plus 1/3 of this new integral. But this new integral, notice the nice thing about it, is the combined degree is not 5, is now 3. So I dropped the degree by 2. And that means that if I continue to do that, next time I should be able to compute my integral. But what I'm going to do then is I'm going to add this 1/3 on both sides, and I get 1/3 plus 1 is 4/3 of I equal these other two terms. 1/3 of the secant of x tangent cubed of x plus 1/3 of the integral of the secant of x tangent squared of x dx. So now you see what I can do is multiply times the reciprocal of 4/3 on both sides, which is 3/4. And what's going to happen is 3/4 times 1/3 is 1/4. So I is just equal to 1/4 of the secant of x tangent cubed of x plus 1/4, again, the integral of the secant x times tangent square of x dx. So now we have to do another integration by parts for this other one. So what would you do? I'm just going to set it up and I'm going to give you the answer after that, so we don't have to go for hours in this video. It's already pretty long. So what I'm going to do is I'm going to look at what thing can I actually integrate. Well, I can integrate a secant. You see again the odd power of the secant. So I have to combine it with a tangent, so I can make this basically a u equals secant would be the substitution, but in this case it's just straight up the integral of the secant. And now here on this other side, I am going to have u is whatever is left over, which is going to be a tangent, and then du is going to be secant squared of x dx. So I want to put it in. So 1/4 of the secant tangent cubed plus 1/4. And now in here, I want to put my integral here. uv, secant tangent, minus the integral of the v du. So v and then du, which is going to be the integral of the secant cubed of x dx. All right. Now, we have to play the same game we did before. So let me separate things out. And I'm going to call this guy here, this integral here, I2, if you will. So from this integral here, I can do the substitution secant squared being equal to 1 plus tangent squared to recover this integral, a multiple of this integral I2. And I played the same game of moving it to the other side and then evaluating the integral. But as I said, I'm going to put this one in the computer so we can skip the step, which is the same as we did before. We got I, moved it to the other side, and then multiply. Now again, when I'm doing I2, I want to get this one. This one is going to be the same as secant of x times tangent, but tangent square, I'm going to write it as secant squared take it back. The secant squared, I'm going to write as 1 plus tangent squared. So it's going to be 1 plus tangent squared of x. And that right there is going to give me secant squared. The integral of the secant is natural log of secant plus tangent. And then for that, the next term is going to give me a another multiple of the I2 that I call here. And I'm going to subtract it or add it on the other side and then multiply to compute that whole integral. Anyways, I'm going to put in a calculator. I'm going to tell you what I get. So as I said, once you play that game, you do that trick. It's not really, I didn't have to do it in a calculator. I just did it on paper. I mean, it's just subtracting and you get 2 times the integral I2. Please go ahead and check, and if not, you can ask me. And so what I get is 1/4, and then this integral itself that I called I2, so that whole thing is going to be 1/2. So I'm going to 1/2 times 1/4 is going to be 1/8 of, and I'm going to distribute that 1/8 secant x tangent x. You can see how that term already appeared here. It just is going to be divided by 2 when you subtract on the other side. And then the integral of the secant that comes up from distributing this, when the integral of the secant is going to be minus 1/8. The 1/8 comes from the 1/2 of the integral and the 1/4 here. Natural log of secant plus tangent. And finally, plus c. I waited to write the plus c until the very, very end, but that's just a matter of that I don't want to be adding plus c every single time, and I still have integrals, so I'm saying I'm lumping those integrals or those constants until I add it at the very, very end. Anyways, that's going to be the video for today. Pretty long, but hopefully very informative.